All right, today we're going to be talking about a homework question where we have a light horizontal spring and we've got a block pressed against it. This is going to be a question that is going to involve several different types of energy and kind of the flow of energy through a system. So we're going to examine that and see what we can figure out here. All right, so we got a light horizontal spring, given spring constant, and we have a block that's pressed against one end of it, compressing the spring. Okay, so we've got a spring and it's relaxed and stretched out, say to right there. Ooh, but then what happens is we take that same spring and we squish a block up against it, and so all of a sudden, oops, can't be losing that. All of a sudden, what's going to happen is our spring is going to be squished back as a block is pressed up against it. All right, and that block, so we've actually then pressed it back this far, and it turns out that that's going to be, in my case, 0.108 meters, and so that is how much. So someone brought this block, set it down, and squished it back and has spring-loaded it, so to speak. All right, so at this point, that's what's happened. Now, when we did that, we stored some elastic potential energy because we did work against the spring and stored EPE within the spring in the process. Okay, and since we know how firm the spring is, it's got a spring constant of 150 newtons per meter, and so since EPE is 1/2 times K times x squared, we actually have all the given information in order to be able to calculate our EPE. Now we'll do that in just a moment. So what I want you to notice right now, though, is that we have some EPE stored in this. Now we don't have any other forms of energy present. It's not moving, so we have no kinetic energy. It's not elevated above a surface, so we have no gravitational potential energy. But we have some EPE stored. So let's just run through real quick the basic transition of energy. Here's what's going to happen. Right now the block has a certain amount of EPE. Well, when we let the block go, when we release it, what's going to happen? Well, the spring is going to spring it, and it's going to spring forward and slide along the table or slide along that surface. And so the EPE is going to be transformed into kinetic energy. So however much EPE we have, then it'll be transformed into that much kinetic energy. Well, the problem is then that it's sliding along a rough surface. And as it does, it says that after the block is released, it moves this far to the right before coming to rest. And so clearly it's a rough surface, and there's some friction that begins to slow the block down. So the EPE transitions to KE, but then that immediately begins to be spent doing work against friction. And it eventually comes to rest. And so now when it's at rest, of course, then it has no energy again. So we're back to 0 joules. And we've got some amount here at the beginning that we'll find out. And what happens is it transitions from having that EPE to having all that KE, but then in that transitional process of coming to rest, it's doing work against friction. So work against friction. And that's that transition between here and there. Now, here's what we can see, though. We had this much, because if you had some energy and then you've lost it, okay, and I'll tell you what, I'm going to go ahead and pause and calculate this for just a moment. All right, and so I know that my EPE is going to be equal to 1/2 times 150 times 0.108 squared. And when I take all that and plug the numbers into my calculator, or my abacus, or whatever it is that you're using, I see that I get 0.8748 joules of energy. Now, of course, that's my answer. Your answers will vary just as your numbers and givens in your questions vary. Here's the deal, though. That means that at this point, I have 0.8748 joules of EPE. And then we release the block, release, and off it goes, and it springs forth with, coincidentally, and actually not coincidentally, 0.8748 joules of kinetic energy. And that's because the energy is transformed from one kind into another. Now, then it comes to rest. And so at that point, we've got 0 joules, which means we lost somewhere in there 0.8748 joules of energy. Well, where did you lose it? What did you do with it? What did you spend it on? Where did it go? You spent it doing work against friction. Okay? So at this point, I can say to myself, hey, that means that the work done against friction was equal to 0.8748 joules. Okay? And so there you have it. Now, why would I want to know that? I've sort of jumped ahead just a bit because I noticed that at the end they actually asked me, what is the coefficient of kinetic friction? You'll remember, and we see that the block moves 0.271. All right, so the total distance that it covers then is actually going to be 0.271 meters. So I'll write that down as well, that D equals 0.271 meters. And what we're actually asked for is we're actually asked for mu. So mu equals question mark, and that's what we're seeking. Now, mu, we remember from our previous work, or from our previous chapters, is equal to FF divided by Fn. Okay? This is how mu is calculated. And it's no different now. Which means, though, that in order to calculate mu, I'll need a value for FF and I'll need a value for Fn. But if I know the work done against friction, you remember that any work is force times distance. And so the work done against friction is equal to the force of friction times distance. Now, if we want to be picky and particular about this, this value should be negative. The work done by friction always is, because it is always a loss of energy. I had this much energy, and now I don't. Now I'm down to 0. And so clearly that was a loss. That was a negative value, which means that one of these should be negative also. And that simply means that they're in opposite directions. Friction will be acting to the left, and the distance covered will be acting to the right. With all that in mind, the sign will not matter when I go to put it in my mu calculation, because FF and Fn are in different dimensions. FF is acting in the x dimension. Fn, of course, will be acting in the y dimension. So even though that should have a negative sign in terms of its work calculation, I'm going to go ahead and look ahead and neglect that for my calculation there. All right, so with that explanation in mind, yes, the sign matters when we're talking about the work, but not when we're talking about the mu. That's always going to be given with positive values. It is a ratio. It is not directional. Okay, so work done against friction is 0.8748. All right, so at that point, I'm going to take my original value for the work done by friction. Again, remembering that that's definitely a negative value, but I'm going to go ahead and neglect the negative signs. 0.8748 will equal FF times D, which is 0.271. And when I do the division there and solve, I'll get that FF, in terms of its absolute value, is equal to 3.22804. So FF is equal to 3.22804 newtons. And since we are going to be using this for our homework site, we'll want to keep all of those decimals. Ordinarily, that would be too many just in terms of our significant figures. But since the computer cares not about significant figures, it only wants decimal after decimal. We'll give it what it's after, decimal after decimal. So there's FF. Great, we're halfway home. Now all we need is FN. So let's consider just for a moment a quick free body diagram. I'll just go ahead and do that on there. I'll just switch colors. We'll do that in a nice pleasant green color. Remember that once this thing is moving, so pretend that it's already been released and it's in motion, we will have FG acting downwards. We will have Fn acting upward. And of course, once it's moving, then friction will be acting backward. At that point, the force of the spring will no longer be present because it will have applied its force and the block will be sliding in motion. So friction will be the only one acting in the x dimension. It'll be the net force, and that's why it will be slowing that down. But then you see in the y dimension, Fg is going to be equal to Fn. Okay, well, we need Fn, and we can find that from calculating Fg. And you'll remember, of course, that the weight of any object is equal to its mass times the acceleration due to gravity, wherever it happens to be. So in this case, Fg is going to be equal to its mass, 2.13, times the listed acceleration due to gravity, 9.81. All right, and at that point, Fg equals 2.13 times 9.81, and you'll get a value for that. And I'll just record it down here below. So looking real quickly, turning on my calculator. So 2.13 times 9.81, 20.8953. So that will be, for me, 20.8953 newtons. Excellent. So let's just go ahead and put that in here, 20.8953. Then we'll just do the math and get a value for mu. And the value that I get at that point is 0.154487. Again, way too many significant figures for what was originally listed in our problem, but just right for a computer that's simply carrying out instructions and comparing values. And again, since there's our first non-zero number, you'll want to hold at least 4 of those for your answer. So again, this particular question is all about the transformation of energy from one kind, EPE, to another kind, KE, and then all of that energy being spent doing work against friction. So we've sort of got the idea of energy transformation, but then also energy usage and spending against friction. And that information then allowed us to find the coefficient of friction of the surface and the block. All right, I hope that was helpful, and have a great day.